Good morning, everyone. My name is Holly Ruser, and I'm a National Product Manager here at Graybar. I'd like to welcome you to Graybar's G2 Talk presentation today on the future of data center cabling. This talk is a part of a webinar series we offer each month for our data communication customers. We've got a really great discussion lined up for you today, but before we get started, I'd like to cover just a few housekeeping items. First of all, if you are one of the first 50 people who joined in on this presentation, you will receive a coupon for a free cup of coffee, courtesy of Graybar, as a thank you for your time today. Also, if you notice at the bottom of your screen, you'll see a box for Q&A. Feel free to submit questions throughout the presentation. We'll address just as many of those questions as time permits at the end of the presentation. Lastly, our G2 Talks are all archived on the graybar.com website, so you'll be able to view this presentation again or share it with others. We're happy to team up today with Corning. As a data communications distributor, Graybar works alongside Corning to provide the latest network infrastructure technologies to help prepare you for the future. You can visit graybar.com to learn more about our solutions. At this time, I'm very excited to introduce today's speaker, Brian Roney. Brian's the Manager of Data Center Global Market Development at Corning. He has over 15 years of experience, and he has held various positions, including product engineering, systems engineering, and product line management. In his current role, Brian oversees data center business development for enterprise networks. In 2005, Brian received recognition as the Dr. Peter Bark Inventor of the Year for Corning Cable Systems, and also received his Professional Engineer's License. Brian is a graduate of North Carolina State University and holds both a bachelor's degree as well as a master's degree in mechanical engineering. He also has an MBA from Lenoir-Rhyne University in North Carolina. So without further delay, I would like to turn the presentation over to Brian. Take it away, Brian.
Thank you, Holly, and big thank you to Graybar for allowing Corning to be a part of your G2 Talk series. Today, we're going to be talking about the future of data center cabling. In particular, we're going to start off and look at some of the data center trends, what's driving bandwidth growth, how do we handle those growth with new data rates, and the new technologies that have to support those new data rates, in particular, WDM and parallel transmission. We'll talk about what that path then plays out and looks like as a roadmap, an optical roadmap, all the way out to 400 gig. We'll transition from there and look at some of the new cabling applications, and that major application is port breakouts. We'll talk about why do we do port breakouts, what are they, what issues do they cause in cabling in our data center space. And then finally, we'll back all that up to say, okay, this new technology is creating some new challenge for cabling in the data center space. What is the overall solution that best addresses those challenges, and what are the value of that solution? And we'll talk about the base 8 value prop for cabling our data centers of the future. So just to start with, let's talk about what is driving bandwidth demand. This chart shows you the shipments of servers into our data center space by percentage broken down by speed of those server connections. So traditionally, over the last several years, 1 gig server connections has dominated our data center space. 2015 marks the first year that 10 gig connections, shown in aqua in the graph, will outpace 1 gig connections for new servers that are being deployed in our data center space. What's driving this primarily is server virtualization. So traditional servers in the past have run a single application per device. So a single server would run an application like a print server or file server or mail server or web server. A single hardware or single device could not hold multiple applications. Hence, they became highly underutilized and only ran at efficiencies of 15 to 20%. However, the modern data center is moving to a highly virtualized server environment where we run multiple applications per hardware. This has put a demand on the server input-output connections as these servers are being better utilized in our data center space. Hence the need for servers moving from a 1 gig traditional connection to a 10 gig connection, and then as you see on the graph, to higher data rates in the future of 25 and 50 gig, all the way out to 100 gig over the next 5 years. This strain at the server connection level then puts a strain on the network. So the network is our network of switches that ties together all the servers in the data center to all the storage devices, and then ties us to the data center, the outside world, to that facility that we're trying to communicate with. Those server speeds, as they increase to from 1 gig to 10 gig, now put that strain on the switch, and the switch speeds, which have traditionally been dominated by 10 gigabit Ethernet connections, now start to introduce 40 gig connections in those switch speeds. Over the next few years, those server connection speeds grow even more, traditionally to a 25 gig, probably mostly copper connection, and then that puts the strain again back on the switch network, hence the growth of 100 gigabit Ethernet over the next 3 to 4 years in the data center space. So this is great. You may not be experiencing a lot of 40 gig and 100 gig connections in your data centers today, but it's coming. It's coming over the next couple of years, and we'll see that primarily as switch-to-switch connections in the data center space. So wonderful. How do we cable these things? Well, traditionally, as data rate increased in the data center, we would simply take the transceiver technology and change the bit rate, aka how fast we actually turn off and on the transceiver. In serial communication, we use digital transmission to turn the transceiver off and on to create ones and zeros in our data stream. So simply said, if I want to change my data rate from 1 gig to 10 gig in the data center, I simply turn off the transceiver 10 times faster and produce 10 times more data in a given period. This has traditionally always worked for us in the data center space as we move from 10 meg to 1,000 meg or 1 gigabit Ethernet, and then from 1 gigabit Ethernet to 10 gigabit Ethernet. However, we have run into a barrier with transceiver technology. That barrier is that these light sources, these lasers that we plug our cabling plant into, they don't want to be modulated or turned off and on much faster than 28 gig at the current time. There is development in that space that gives promise to future speeds of 50 gig and maybe even beyond that with some of these light sources. However, today in an economical, manufacturing capable environment, 28 gig is about our limit of being able to turn off and on these transceivers. So how do we get to 40 gig? How do we get to 100 gig? Well, we can't do it in the traditional way, which is just turn things off and on faster. In the analogy on the screen, traditional data rates, we just change the speed limit. If data rate is the speed limit, then we can't just increase the speed limit of the traffic flow. We have to pull out one of two tools. The first tool is WDM, or wave division multiplexing. Wave division multiplexing is simply taking multiple streams of lower speed transmission and combining those and pulling those together or aggregating those together to create a higher data rate. So in the example of 40 gig, we take 4 10 gig streams and transmit 4 10 gig streams over the transmission media and then combine those on the other end. So WDM takes 4 10 gig transceivers, 4 10 gig light sources at different wavelengths or different colors of light. Inside that single transceiver, we then combine those 4 data streams into a single data stream at 4 different frequencies or 4 different colors of light. And we combine that over a single strand of fiber to transmit down the cabling media into another transceiver where it's then split out into its 4 wavelengths and received over those 4 individual channels. This is not a new technology. It's been used in the outside plant world for many years where the cost of putting in a new cable is very prohibitive. However, this has not traditionally been used inside of our data centers because it is very costly on the transmission side. If I were to use the analogy shown on the screen, if we're trying to move people or data, in this analogy, people represent data, and I'm trying to move them from point A to point B, say over a bridge, I would simply take the car, which is our data rate flow. I don't increase the speed like I would to go from 1 gig to 10 gig. I simply pack more data over the same rate. So I'm packing 4 data streams. I'm packing 4 more people per car. The car is still moving at 10 miles an hour or 10 gig, but I put 4 people or 4 times the amount of data in that car. The second tool traditionally used is parallel transmission. In parallel transmission, I still have 4 independent data streams, but each one of those data streams are operating at the same wavelength. In this case, maybe it's 850. In a single mode case, it would be in our 1300 region. So the analogy here is I'm not changing the speed. I'm not changing the number of people per car, but I'm increasing the number of cars to get the same amount of people across the bridge. So those people have to be traveling on their own lanes, and so I have to increase the number of lanes across that bridge. Same is true in our fiber. We have to have more physical media to transmit those packets. So instead of a 2-fiber connection at our transceiver, we could see 20 fiber connections, or in the case of SR4, which we'll talk about, it's an 8-fiber connection to the transceiver. So as shown in the diagram, there is a 12-fiber MTP connection there, of which we're using 8 to transmit, over 4 in each direction. So those are the main 2 tools that we use to kind of ramp up or bump up our data rate, WDM transmission or parallel transmission. There's a third that we won't talk about today, which is multi-level modulation. Simply means data compression. That tends to be the most cost-ineffective solution out there. Hence, it'll be the last tool we use in data transmission to pack more data per bit rate. So how does this play out? These 2 technologies play out in a roadmap. This slide on your screen kind of shows a nice little layout of the optical roadmap that takes us from 40 gig to 100 gig. I'll leave out 200 gig here, but we could put a column for 200 gig in the future. And then the current speed under discussion, which is 400 gig. The rows themselves represent various solutions that we've talked about. The first 2 rows represent the multimode solutions. First row says duplex, OM3, OM4. So that means I'm delivering a 2-fiber connection over multimode fiber. These are our WDM solutions. And yes, WDM traditionally has always been done over single mode, but in our data center space, we're starting to see that show up in multi-mode applications as well as a more cost-effective WDM solution. The second row shows parallel multi-mode OM3, OM4 fiber. Again, these are the multiple fiber application, greater than 2 fiber applications. So in these applications, I'm delivering the MTP connector or the MPO connector all the way into the transceiver. Likewise, I have those same 2 technologies repeated at the bottom of the page, except now over single mode media. So we have a duplex multi-mode 2-fiber connection, as well as a multi-fiber connection for parallel single mode on the last row of this table. So how does this work? So at 40 gig, if we look at that 40 gig column, when my IT or SAN network team comes to me and says, hey, I need a 40 gig connection, in the future when they come and ask me for a 128 gig fiber channel connection, it's no longer adequate, if you will, to say, okay, I've got that covered as a single mode or multi-mode. No, it has an impact whether they're doing parallel or WDM applications, because now I may be required to deliver that MTP all the way to the transceiver. So for example, in the 40 gig column, the first duplex solution we have a couple of solutions there in black text. The black text simply means that this is not IEEE, an IEEE standard. So Ethernet is controlled by the IEEE body. The things in blue are approved parts of those standards. The things that you see in black are not in those standards, but rather in engineered solutions from a particular switch vendor or a particular transceiver vendor. So BiDi, 40 gig BiDi is a solution that Cisco uses for 40 gig communication over 2 fibers. It uses multiple wavelengths to communicate over our multi-mode fiber. Likewise, there's a SWDM4 solution that will be coming out later this year. This is a short wave division multiplexing over 4 channels, so 4 different wavelengths, starting at 850 on a 30 nanometer spacing. So those 4 wavelengths would be able to support 10 gig each to give us our 40 gig stream over a 2 fiber connection at the transceiver. Likewise, we have SR4 in the second row of the 40 gig column. SR4 is the standards-based solution. Simply said, it is the 4 by 10 gig parallel version. So if it's in that parallel row, we know we're delivering an MTP all the way into the transceiver. The first row was an LC duplex connection. So SR4 is a standards-based solution and offered across all switch vendors. So it doesn't matter if I'm Cisco or Arista or Juniper or Brocade, I'm going to still have an SR4 solution set across all vendors because it's standards-based. There's also an extended reach version of that, ESR4. Again, since this is not a standards-based solution, every vendor brings this to market with a different terminology. Cisco calls this CSR4, as in C for Cisco. That simply extends the reach by about 3x of the standard reach of SR4. Likewise, Arista brings this to market as an X for extended, XSR4. So again, once we get out of the standard terminology, like SR4, and we go to these black labeled solutions, every vendor could bring this to market as a different label of the solution set, which can be somewhat confusing. Likewise, we got duplex single mode solution. Standard solution is LR4, which is good all the way up to 10 kilometers. A lot of data center spaces say, hey, that's way too expensive. I don't need 10 kilometers. I only need, say, 500 meters in some of these mega scale data centers. In that case, they've also released kind of a lower grade solution of LR4L, which is LR4 Lite, which is a 2 kilometer solution. And again, each vendor may slightly change the name here, but it'll be a 2 kilometer single mode solution. And then finally, the last solution in the table for 40 gig is PLR4. This is a parallel over single mode. So again, it's 8 fibers of communication or 4 channels, but it's using single mode as that media and still the MTP connector at the transceiver. Traditionally, this is used in our hyperscale data centers. Those data centers like Microsoft or maybe a Google or a Facebook would use parallel transmission over single mode. Traditionally, if you look at it, parallel is going to be the lower cost solution over WDM. And we'll look at some of those economics on the upcoming pages. However, not all of our data centers can use the shorter reach of multi-mode. In particular, the hyperscales, the very large data centers, have to go to a single mode solution, but they're still going to typically pick the lower cost solution, which is the single mode parallel. This repeats again at 100 gig. We have BiDi and SWDM4 repeating there. We have parallel repeating again. We see a Gen 1 and a Gen 2 solution for parallel. So Gen 1 was SR10, which is a 10 by 10 gig solution. So that's a 20 fiber connection at the transceiver. We used a 24 fiber MTP to accomplish that. Gen 2, which is coming out now, is again SR4, which is 4 by 25 gig. You might ask yourself, why the confusion? Why have a Gen 1, Gen 2? When 100 gig was originally released, the ASIC, the chipset inside of all these switches were all based off of 10 gig electrical speeds. So we matched the electrical to the optical speed to keep the cost of the transceiver down. So we used a 10 gig ASIC to develop our 40 gig solution platform. So it made sense to use a 10 gig lane speed. Well, also when we did 100 gig, the only ASIC we had at the time was 10 gig ASIC. So the only option we had to make a viable solution was to also make the optical speed 10 gig as well. So hence we had SR10 as the first gen solution. Now that hit the market, many of you probably never even used an SR10 transceiver. The typical form factors there were Cisco had a proprietary CPAC form factor of their transceiver. Others used CFP transceivers, which were extremely large and maybe only 2 or 3 per line card on a switch instead of our traditional 32 or 48 ports in a line card. However, that gave way to new ASICs, which are our newest generation that we call the Tomahawk ASIC, created by Broadcom. And Broadcom then sells that to all the switch vendors to put inside their switches. And now all the electrical speeds can run at 25 gig electrical speed inside the switch. Thus, I need to match the optical to that ASIC speed. So the SR10 gives way to SR4 for that reason. So all of our 100 gig switches will be based off of 25 gig ASICs. All of those are being launched in the market later this year, later this year or early next year, according to the vendor. Hence, all of the WDM applications will be 4x25, as well as the parallel will be 4x25 gig. And I'll show you this on the next slide, some of these adoption of some of the 40 gig speeds, and we expect the same to be true at the 100 gig speeds as well. We have, again, repeat of single mode WDM over 2 fibers, as well as parallel over 8 fibers with PSM4. PSM4 is being used today in field trials and being fully deployed this quarter by the likes of Microsoft, as they've publicly announced. So we see this repeat again at 400 gig. Question mark for duplex multi-mode connections at 400 gig. Not sure what that solution would look like at this time. But most vendors say for the parallel solutions, it's pretty simple that if I can put a BiDi or a SWDM4 solution at 100 gigs over 2 fibers using multiple wavelengths, then I could take that 100 gig connection and place that in parallel to get to 400 gig, which is the Gen 3 solution that we see at 400 gig, the SR4, 4x100. So a lot of the lower data rates, the WDM applications that are there, will be used in conjunction with the parallel solution to get us to the higher data rates of 200 and 400 gig. Likewise, we have WDM again for duplex single mode and PSM4 again for parallel single mode. Now this map is kind of overwhelming. There's a lot of terms on it. The moral of this story is we use our 2 tools, WDM or parallel, to get to these higher data rates. And we either do that over single mode or multi-mode for all the various data rates. However, the important note on this slide is that each one of those solutions simply culminate in really 2 solutions. I've got to deliver either 2 fibers with an LC connector at the transceiver, or I have to be able to deliver 8 fibers to the transceiver. Now, yeah, there's some speed bumps along the way, like SR10 was at 100 gig. However, those are speed bumps. They're not the final destination. They're only an interim solution while some of the ASIC development occurs. So whether we're talking about parallel multi-mode or parallel single mode, the final destination is 8-fiber connection at the transceiver. Now this next slide really starts talking about what is the current adoption rate of these various technologies. And I could have shown this for 100 gig, but I just chose the 40 gig adoptions. And you will see this is data from a consultant, Light Counting, who kind of shows what is the current adoption from 2010 through 2014, which is historical data, and then 2015 to 2021, which is the forward-looking data. So you can see that SR4, which is the blue line, continues to be the dominant space inside the enterprise and mega or hyperscale data center spaces. It's the most economical, cheapest solution in that space. So, of course, it's going to be the most popular. The next one is the green line, which you see kind of taking off in 2016, which is the WDM multi-mode solutions. Again, extremely economical as compared to the single mode solution. So if my reaches or distance inside the data center kind of meets that threshold of 100 to 150 meters or 300, 400 feet, these multi-mode solutions are the most popular. And then finally, we see our mega customers, the hypers, really looking at parallel single mode and WDM single mode, the red and the purple line. I would note that the article or the study done by Light Counting does note that parallel single mode is highly underestimated at these 40 gig volumes. There's a critical vendor for one of the hyperscales that they do not get data from, that they know they're missing that data on. So the PSM4 line, the red line, should be higher than it's shown here in the diagram. So we've talked a lot about Ethernet, but what about Fibre Channel? I'll just quickly say that Fibre Channel is no different from Ethernet. We traditionally had a 2-fiber connection at the transceiver, all the way up to 32 gig Fibre Channel, which is the third row in this chart. However, the next data rate of 128 gig is not a 2-fiber connection in the SAN network. It is a parallel connection. As you see by the aqua or blue text, it's a 4 by 28 gig connection to get us to our 128 gig data rate. So just like the Ethernet that has to pull out the WDM and parallel tool, so does our Fibre Channel in our storage area networks. So two of the next three speeds, 128 gig and 256 gig, will both use parallel transmission, 8 fibers into the transceiver via an MTP connection. Likewise, I give a nice example at the bottom of the page of kind of a leader in that space in the SAN networking is Brocade. They recently released their 16 gig Fibre Channel line card, which you can see by the table above, should not need MTP connectivity into the transceivers. But each one of those ports on this line card are an MTP connection. And they simply did that for the reason of trying to fit 64 ports in a given line card. So it wasn't a data rate thing as much as a line card density and getting all the transceivers packed on that line card to utilize all the ports in the electronics or on the ASIC. They needed to fit 64 ports in there. 64 ports of SFPs do not fit on the line card. So they went to the QSFP form factor, the parallel form factor, put 16 of those on there, and then I have to break out that 16-port connection into 4 duplex ports each. So those 16 physical ports turn into 64 addressable ports for that line card, each running at 16 gig. So speaking of breakout, that is a new trend that's happening in our market space. I know as I go out to talk with customers that are deploying 40 gig, I sometimes get the cross-eyed look saying I'm not actually deploying 40 gig. I'm just deploying 40 gig to break it out into 10 gig. And here's why. So if I'm a data center operator and I need to expand my 10 gig network, I need to bring in more switches, more connectivity to supply more connections to servers or storage. I've got two options. On the left-hand side, I could buy a native 10 gig line card that has 48 SFP ports that I could plug my optics in, and then buy 48 transceivers to plug into those various ports, and use LC jumpers to make my connection in the link. Or I could buy, on the right-hand side, a 40 gig line card for that same switch, same chassis. It's only got 24 ports per line card, so I'm only going to buy 40 of the SR4 optics to place in there. However, those 24 ports now break out each port into 4 10 gig ports, so that one line card supports 96 10 gig ports, 4 times 24. Well, how does the cost break down on that? The cost breaks down on the bottom of this slide as two options. First option is our native 10 gig port. As you can see, if I buy that line card at $44,000 and put 48 transceivers in there, each one of those 10 gig ports cost me around $1,900. However, I could have bought the 40 gig line card, the second option in that table. That line card is going to cost me $55,000. And each one of those transceivers that I need to put in there, the SR4 transceivers, are roughly $3,000. So I get a total cost of those transceivers of $72,000. However, I'm not dividing this by 24. Each one of those 24 ports is 4 by 10 gig breakout. So this line card total cost is now divided by 96, because I don't have 96 10 gig ports out of there. So that's a $1,300 cost per port. So by buying 40 gig optics and using them in breakout mode to run 4 by 10 gig, it's 30% cheaper per 10 gig port than buying native 10 gig today. So a lot of data center operators have caught on to this and have started deploying 40 gig, even though they really don't need 40 gig. They just need high density 10 gig connections today because it's 30% cheaper per port. It's also a clear migration path when they do need 40 gig. They don't have to repurchase the line card or the optics. They're already been paid for at 10 gig. So it's a very cost-effective migration path. Likewise, I can get 50% less power per port. A QSFP 40 gig transceiver consumes about the same power as two SFP 10 gig transceivers. However, it replaces 4 10 gig transceivers. So again, the power consumption of the switch is cut in half from the optics standpoint. Of course, the ASICs and those type devices still are consuming the same amount of power. So it's a more cost-effective migratable path. You can't do this with WDM applications. You can only do it with our parallel, either single mode or multi-mode applications. So again, another reason why parallel transmission and breakouts are being used in our data centers today. That does create some challenges with cabling, which we'll talk about some clean ways to handle those breakouts in the second section. So finally, to kind of end our discussion on this technology piece, we can look at parallel versus duplex solutions from a total cost of ownership standpoint. So traditionally in our data center space, we never had to worry about total cost of ownership for between the two departments, meaning between the folks that are making the purchases for the electronics, the switches, and the transceivers, and the infrastructure team that's buying the structured cable plant. All we needed to know was, is it multi-mode or single mode, and I've got to deliver a 2-fiber connection to that transceiver. Again, we mentioned before that's not good enough to know that anymore. We have to be talking between those two departments and those two groups to understand, okay, yes, I understand you need a 40 gig connection to those racks, but is that a parallel? Are you using something like SR4? Are you using a WDM solution like BiDi or SWDM4? Because that connectivity and that demand on the cable plant is totally different. Also might need to know, hey, I'm going to run 10 gig connections, but I'm actually buying 40 gig optics and using them as breakouts. So we have to start looking at this as a combined cost. I don't know how many times I've walked into a data center and started talking about 40 gig, and I'm talking to the infrastructure team, and they say, we're not going parallel. It's simply too expensive. My cabling bill per link goes up 3 times what it used to at 10 gig because of parallel transmission takes 4 times the amount of fiber. And I said, have you looked at the total cost of ownership? Meaning bring the cost of that structured cabling and transceivers together and look at them as a combined cost. Because yes, it may be cheaper for you to buy the structured cabling for a WDM solution, but the total cost of ownership, you could save 30–50% by going to parallel because the savings are going to be on the transceiver side, on the electronic side. So we did a little exercise. We do this often with customers where we look at a parallel versus duplex solution set. We take their cost of their cable plant and the cost of the transceivers that they would get from their switch vendor, and we put that together in a kind of a total cost of ownership view. What you'll see in this slide is the structured cabling is the blue graph in these bar charts. Then we look at 40 gig optics. What is the cost of those 40 gig optics kind of in that green stacked on top? And then finally, the red is the patching or the patch cords that come from my structured cabling into those transceivers. Now, traditionally, what we've done is looked at that at a single data rate at 40 gig. So, for example, in this slide, you can see the first two technologies, multi-mode duplex, meaning a WDM, versus multi-mode parallel, meaning an 8-fiber connection at the transceiver. If I looked at a single data rate of 40 gig, there's not a lot of difference between a duplex solution versus a parallel solution. Yes, I'm paying a lot more for that WDM transceiver for WDM, but I also had to pay a bigger chunk to get to the parallel for the cable plant side. However, when we add on a second generation, meaning the 100 gig optics on top of this, you can see that the story changes pretty dramatically. What most data center owners should be considering is this idea of multi-generations with their structured cabling. Hopefully, I don't put in the cable plant just for one data rate and have to rip and replace. You're guaranteed when you go to the next data rate that you're going to have to throw away transceivers. You simply can't reuse those electronics. But you have at least a really good shot of reusing the cable plant. So I want to at least look at 2 generations of optics with the cost of my cable plant, which now gives me a pretty drastic picture between the 2 different technologies and a lot lower cost of ownership in that space. Hence why the large hyperscale customers have traditionally used parallel optics. Microsoft, Facebook, those customers have chosen to put in parallel optics for the low cost of ownership. And another good reason why we saw those adoption curves of SR4 being so strong in this space as well. So what is this kind of summarized view of this technology roadmap of the transceivers culminate into? And it's this poor graphic display that I've put together here on the screen of a roundabout. In other words, no matter what road you travel, there's a lot of uncertainty in that transceiver space. There's a lot of uncertainty from these IT and storage area network teams of which vendor they may go with, of which technology they may go with. Are you going to go with BiDi? Are you going to go with SR4? Are you going to go with SWDM4? On the storage side, are we going to be putting 128 gig in the next 6 years in our SAN networks? Just a lot of uncertainty. But that uncertainty, as we looked at the roadmap earlier, converges on a simple fact. If I'm a structured cabling person, I have to be able to deliver 2 fibers at the transceiver or 8-fiber MTP at the transceiver. So with that said, I have to ask myself, is that the smartest way to cable? Am I doing the smartest cable plant today to be able to support this uncertainty? And that's really what I want to talk about the Base 8 in the next 10 minutes or so, just to talk about what is the next generation cable plant look like to be able to support any of this uncertainty that may come. So traditionally, our data centers are using pre-terminated assemblies, meaning a MTP backbone trunk that then plugs into breakout elements. We call those modules or cassettes. So those MTPs would go from point A to point B, plug into these cassettes that break them out into LC connections to then connect via jumpers into our transceivers in our switches. Traditionally, that MTP of choice has been the 12-fiber MTP connector, meaning that there's 12 fibers in one of those connectors, and we break that out into 6 LC duplex ports in the module. What I'm going to show you next is a small change in that statement. We're not discussing base 12 as the future cable plant that provides the most value, but rather a base 8 cable plant. Now, base 8 seems like a logical discussion when we talked about 40 gig, but you'll see as we look at that roadmap, it applies at 100 gig, it applies at 200 gig, and it applies at 400 gig as the final destination for all of those speeds. So again, there's road bumps along the way, and we'll talk about some of those as we look at the value of this solution. So at Corning, we just launched in the past few weeks our Edge 8 product line, which is, again, a base 8 based solution. So again, all the MTPs, all the breakout modules, all the connectivity are built off of the 8 fiber base MTP connector, again with the thought of build the backbone to support any of the technologies, and then just use the elements on the end to either handle WDM or parallel applications. So let's talk about this base 8 value. I'm going to talk about 5 key cornerstones of the value that base 8 provides over base 12 solutions. First cornerstone is cost savings. So with traditional base 12 cabling, I've got 2 options. When I go to parallel optics, I can simply take my 12 fiber connection from my patch panel and patch directly into transceivers and waste 30%, 33% of my cable plant. So it's inefficient in the fact that I'm paying for fiber that I'm not utilizing in my backbones of my cable plant. The other option I have shown here on the screen as this top diagram, which we call conversion modules. So conversion modules simply take 2 12-fiber MTPs on the rear of these modules and convert them to 3 8-fiber MTPs on the front of our patch panels. Effectively, a 24-fiber trunk can now service 3 40-gig links. These are our 3 8-fiber links, and not waste any fiber in those backbone trunks. So I have to pay for this extra connectivity of that conversion module in order to utilize all my fiber in my backbone. Now, selfishly, I'm a cable vendor, so I love parallel to win over WDM. I think there's pretty good evidence of why we like parallel. And what our goal is to try to optimize the cable plant such that we don't have a suboptimal cable plant in parallel optics, meaning I'm not paying for fiber I'm not using, or I'm not paying for extra connectivity cost to use that fiber. So if you look at the bottom of the screen, that's a base 8 24-fiber trunk. Again, notice that trunk is now 3 legs of 8 instead of 2 legs of 12. But now, instead of having that conversion module on my patch panels, I simply have a MTP adapter, just an MTP pass-through panel. So ultimately what that does is reduce the overall number of MTPs in the link, which effectively for a vendor lowers their cost. So overall, we can produce 30% less MTPs to create these 3 links, which results into a 15 to 25, all the way up to a 50% cost savings. And this is the graph that shows the actual cost savings. So the top line represents the cost savings of putting in a base 8 cable plant versus putting in a base 12 cable plant with conversion modules. So for example, if my system was 100 feet long, so roughly 30 meters long, if I followed from the 30 meters on the x-axis up to the orange line, I would save over 50% of my cost. So if I would have deployed base 12 with conversion modules, I would have paid, let's say, $2 for that link for the fiber cable plant. Now I'm going to pay $1 for that link for the fiber cable plant. So again, a 50% savings over the base 12 with conversion module solutions, cutting my cost in half. Massive savings. Likewise, for base 12, with the idea of, okay, I know those conversion modules are going to let me use all my fibers, but I'm willing to throw away fibers. So I'm going to put in a 12-fiber cable plant and plug that 12 fiber directly into the transceiver and just throw away 4 of the 12 fibers. That cost savings turns out to be about 25%. So again, by not throwing away 33% of the fiber, I'm going to save 25% per link. So again, not as cost savings as the conversion module story, but still very attractive. If I can cut my cable cost by 25%, it seems very attractive. Now you might say, why would a cable vendor want to cut cost of the links? I want to cut cost of links because I don't want there to be a sub-optimized solution for parallel because of our cable plants that makes the overall return on investment lower for parallel over WDM. So we want to make parallel as attractive as possible. Again, the migration piece, of course it migrates really well to SR4, but again, when we start looking at things like SR8, which is a 16 fiber connection at the transceiver, we still can do that with a base 8 with these Y jumpers, meaning still 2 8 fibers out of the patch panel, and then plug that into a 16 fiber at the transceiver and utilize 100% of my connectivity. I could have done that with base 12, taken 2 12s out of the patch panel and done the same thing, but again, I'm going to be wasting some of the fibers. So just a couple more points here, and I'll open up for questions. So again, another advantage of base 8 is eliminating those conversion modules also eliminates attenuation. So for example, in a base 12 cross-connect environment, the connector loss is about 2 dB or half a dB per patch panel. That overall reduces my distance of 40 gig from what the standard says is 150 meter reach down to 110 because I've exceeded the connector loss of the standard, which is 1.5 up to 2 dB. If I did that same connection, same distance with base 8, now my connection loss is only 1 dB, so I cut it by 50%, and I've improved my overall length capability by 70% from 110 meters to 178 meters. So that lower attenuation of the link by reducing those conversion modules results in overall a longer distance capability. Finally, the last solution here is a jumper complexity. So jumpers themselves and an MTP cable plant is a MTP pin or MTP pinless. Sorry for the phone ringing in the background. Is a pinned and pinless MTP. So traditionally in a base 12 cable plant, our trunks or the structure cabling is always pinless. So it simply means when I'm trying to do a direct connect or transceiver to transceiver, I need a pinless MTP jumper. When I go to a point-to-point, that jumper from patch panel into transceiver needs to be pinned at the patch panel, but again, pinless at the transceiver. So it's a second configuration of an MTP jumper I need to support parallel optics. Finally, if I look at a cross-connect, meaning I have one jumper in there at the far right that has to go patch panel to patch panel, that jumper needs to be pin to pin. So to support all three architectures in a base 12 cable plant, I need 3 different jumper pinning configurations. And so again, instead of just fiber type and length, now I have pinning. And oh, by the way, it's important that I don't go try to shove those connections into my transceiver as I would damage that transceiver. Finally, with base 8, we eliminate all that by pinning the trunks. Now all our jumpers are pinless. So the final value here is really port mapping and port breakouts. We said all these transceivers are 8 fiber base, and you can see that this 8 fiber system will allow you to do that very cleanly. So those are really the 5 tenets of base 8. We get lower loss, which increases our distance, lower cost, 20 to 50%. We get a clean migration path. We get a 67% reduction in jumper complexity, and finally, better port mapping for our high fiber count base 8 switches. So for that reason, Corning has invested highly in a base 8 cable plant to go alongside of our base 12 cable plant to support data center current speeds and future speeds in the data center space. With that, I'll turn it back over to Holly for a Q&A session.
All right, Brian, thank you so much. It was an excellent presentation. At this time, we're going to go ahead and address some of the questions that have been submitted. We've got enough time to cover several, actually. So as a reminder, you can submit a question. We already have some that have come in, but you can submit a question using that Q&A box at the bottom of your screen. If we don't get to your question, we will answer it. A Graybar representative will follow up with you after the presentation. So go ahead and jump to the first one. The first question we have is In large data centers, I'm seeing mesh backbone configuration with multiple backbone cables with fiber strand counts of 576 and 864. Has Corning developed cabling, splicing centers, and patch panels optimized to handle these large fiber strand counts?
Very good question. As we see more and more spine and leaf or fabric architectures in the data center space, we see fiber counts really skyrocketing. And yes, we have solutions in our pre-terminated as well as pigtail, meaning MTP one end and blunt on the other end for these data center campuses environments, as well as large fabric environments that allow us to go all the way up to 864 today, and we have plans to extend that beyond 864. So we have plenum solutions that go all the way up to 576, and then riser ratings that go all the way up to 864. And again, we have plans to go beyond that up to 1728 and even over 3,000 fibers for some of these high fiber count fabric supports in our spine leaf or colos type environment.
Okay, great. Thank you, Brian. The second question we want to address is how do you migrate from existing base 12 cabling to this new base 8 rather?
Yeah, migration is always a question of concern. And just to be clear, this 8-fiber connector is a 12-fiber pitch, meaning the middle 4 fibers are just not populated in the connector. We mold those 4 holes shut in the connector. So the pitch or the alignment of the connector is the same, meaning I could take a 12-fiber connector and one of these 8-fiber MTPs and plug them together, and those 8 fibers will communicate. So it's the worst case scenario is if, as we're mixing base 8 and base 12 in the data center, there's no issues as far as compatibility. That's not true with some of the other high fiber count like connectors that we will be hitting the market, such as base 16. Those holes will not align because there's a different pin spacing. So again, migration is a concern. Some people have said, I'm willing to migrate these into the same base 12 housings, your edge housings that you have today. Some customers have said, I will migrate this, but keep them in separate racks to keep the customers from being, or the hands-on team from being confused. And some people have said, you know what, I'll just do it in different cabinets altogether. Forget the 4U boxes, but as I put in a new pod or a new data hall, I'll start then with the base 8 cable plant. But, it's really up to the customer and the comfort level of the customer. Greenfield to me is a no-brainer. Brownfield is really based on a customer-to-customer specific thing. But again, the alignment is there. So worst thing is happen is you plug in 12-fiber connector and say, why are only 8 of them lit up? We do use color code to try to help visually distinguish between the 2 connectors because they are the same form factor and the same style. Okay,
great. So kind of right along those lines as a follow-up question, does Corning see a base 8 solution replacing the current standard solution of base 12 in the data center?
Base 12 has a long history. It's been more than 15 years being sold into the data center space, so I don't see it immediately happening. I do see that a lot of base 8 customers will start to see the value of base 8 and want to prepare that backbone to be most optimized for parallel, knowing that it's coming. They might not be using it at 40 gig or even 100 gig, but knowing that it's going to come at 200 or 400 gig. So I definitely see a transition from base 8 or from base 12 to base 8, but I think it will happen over time, and base 12 will never go away. It's just embedded base is very large.
All right, great. Thank you. So we'll take one last question before we wrap up. And again, I just want to reassure anyone that's asked a question, if we didn't address it, we will certainly follow up with you. A Graybar representative will to answer that question. So the last question we want to answer is if you could just speak to what Corning sees as the best practice for cabling in a large data center.
In large enterprise data center, typically our fiber counts and our pathways are such that we can use preterm MTP to MTP cabling as our backbone, again, trying to, if you will, future-proof that backbone to be able to handle any of this uncertainty, and then using our elements on the end, such as a module, to break that out for WDM or 2-fiber 10 gig applications, or using a pass-through MTP panel with MTP jumpers to support parallel. We do think that base 8 is the smartest way to do that moving forward. There was always uncertainty there about understanding the roadmap well enough to be able to confidently say that base 8 is the right way to go. I think after many months of working with transceiver and switch vendors, we have a clear understanding of this electrical to optical connection, and we can confidently recommend to customers that base 8 is the way to do that. In some of the large-scale, hyperscale data centers, or even campus-scale data centers, that typically it will show itself as a pigtail trunk because of conduit limitations between buildings. So it's an MTP on one end and blunt cable on the other end that gets pulled through conduit. And again, the high fiber count counts just help us maximize the fibers per conduit. And then on the other end, we then terminate in the field with the MTP connector and do the exact same thing. So it's really a kind of a hybrid solution in some of those large-scale data centers. But in our traditional enterprise space, it's preterm, and we're laying these cables into cable tray and don't really have the constrictions of conduit space like we do in some of these campus environments.
Okay, great. Well, at this point, we're just about out of time. Brian, I want to thank you again. It was a great presentation. As a reminder, this presentation will be archived on graybar.com on the website. Again, thank you for your time today. We hope that you will join us again next month for Graybar's G2 Talk. Thank you.
Thank you, Holly.